Alrighty. So let's talk about galvanometers and motors and speakers. And the best way to do this is to just see them, but let's talk about it a little bit here, right? A galvanometer basically is just a loop of wire inside a magnetic field. Now, notice that the current goes this way on this side and this way on this side. Okay, so if you go index finger this way, right, and then the magnetic field is this way, right, from north to south. If you go index finger that way, middle finger to the right, the force will be this way. And if you do the same thing on this side, of course, you flip, the current is now going down, so the force is that way. And what happens is it tends to make this loop twist. So the more current that flows, the more this needle goes that way. Now, of course, there's a spring, and the spring has to be opposed. So the more torque you have, more current you have, the more torque you have, the more torque you have, the more twist you'll get out of this thing, right? So basically, as you send current in, this needle will deflect that way. So basically, all galvanometers are just ammeters at some level, right? But there's a way to use an ammeter kind of as a voltmeter as well. But I don't need to necessarily talk about that right here. This is another diagram. This is if you actually looked at a galvanometer, this is what it would look like, that loop of wire. We're seeing it from above here. And it's actually many windings like that, and then and that's how it gets the torque out of it. The torque doesn't drop off as you twist it, which is a good thing. This is a DC motor, which is not the most terribly good example of it. Let me draw you a better one here. Let's suppose we've got a north pole here and a south pole here. Okay. And then we've got a little loop in here, a little electromagnet in here. This electromagnet we can switch. So we start off like this with a north on this side, a south on that side. Well, these guys repel and those guys repel. So this thing starts to spin, right? It spins around. Well, in the next instant, this north is almost there to the south, and this south is almost there to the north. And what we do, though, is we have an electrical switch. And we use that electrical switch to actually change it, because this is an electromagnet. And just when this north gets to that south, and that south gets to that north, and they're about to be happy and live forever in happiness and peace, we play a cruel trick on them, and that is we switch the polarity of the magnet. So it's again north against north, south against south, like that, right? And it just keeps spinning and spinning and spinning and spinning, right? Anyway, that's the basic idea for a electric motor. This is a speaker. Notice that this thing can move. So this thing can move this way and this way, right? And we cleverly have a little thing called a voice coil, and that's a coil that's like this, right? It's a coil of wire, and we're just seeing the wires here. It goes, this way and this way and this way and this way, right? And if you look at that, those wires are crossing that magnetic field. So the magnetic field will exert a force on those wires. So if the current goes one way, the force is this way, and the speaker exerts. If the current's the other way, then the force is this way, and the speaker inserts, which isn't actually a word, but I'm trying to make it a word, right? In general, if the current goes one way, the speaker moves out. If it goes the other way, it moves in. And then obviously to create a sound, you just cleverly change whatever that signal is, right? It's like, what is that signal, right? It's an audio signal. You send it in there, an amplified audio signal, and it'll make the speaker move in and out. And then finally, one of the coolest things are the arms that run the... actually, if you lift up the platter, if you pull the platter out, underneath is a motor that has... I showed you a motor with 2 poles. This one's probably got like 12 poles under there. It's a very smooth motor. But this is the seek arm, the thing that spins back and forth. So that thing right there is this little loop right there is what I'm trying to draw, right? Those hard drive magnets there, the domains are north up here and south up there, right? And so if you do a analysis of the current, let's say the current is going, I don't know, clockwise, right? So it's going this way there and this way there. You can show, if you go index finger that way, middle finger out of the page, because the north, the magnetic field will be out of that page, right? You'll get a force this way. Okay, then if you go index finger down, right, and magnetic field into that page, you get the force the same way, right? So this what this does basically is it's a way to get a force one way or the other with a current, right? These are just amazingly fast. If you look at the arms, the Seek arms, they've drilled holes through it, right, to minimize the mass of it. Basically, they're trying to reduce the rotational inertia of this thing. It's mounted on ball bearings. It's very, very precise, right? And what it got, I mean, underneath here, there's clever circuitry, and these platters have like little tracks written in them. And one of these little heads here can just read those tracks. And when the disk drive says, gee, I need to go to this sector right here, and that Seek arm needs to sweep across there, it sends a current in here. It moves lickety-split, boom, to where it needs to be. Then it of course stops itself by reversing the current, and then it just stays there. Okay. If you try to move it off that track, it knows because it can read the tracks, and it uses this little current loop to keep itself on that track. It's a very clever thing. What is that? I guess that's negative feedback or something like that. And I'll have one of these in the lab. You can take a look at this thing. I've got one that a kid took apart years ago, and you can actually see it working and moving as the disc spins.